Okay, good day everyone. So you are welcome to this week's lecture of Elements of Modern Physics. Today we'll talk about atomic structure. So that is the topic for today. So in this topic we want to understand the structure of the atom. What is the atom made of? So the structure of the atom is responsible for nearly all the properties of matter that have shaped the world around us. So every atom, our understanding now is that every atom consists of a small nucleus of protons and neutrons, with a number of electrons that are not with the nucleus, that are not in the nucleus. That is, they are not with the proton and neutron. That's our understanding. I'll talk about that later. But one of the early models, or one of the first scientists or early scientists that explained or that tried to explain the structure of the atom was J.J. Thomson. So we'll call the model now the J.J. Thomson model or the Plum-Pudding model. So what is the J.J. Thomson's model about? The structure of the atom all about. Okay, so he said that the atom is like a plum pudding. So that is, it's just like it's a positively charged particle, that the atom is positively charged and that there are electrons. Okay, those electrons are just embedded inside the atom, and the atom is positively charged, so and the electrons are negatively charged because the atom is known to be neutral. So in his own understanding, so he said that the electrons are embedded in the positively charged mass, that is the positively charged nucleus, or not nucleus, he didn't call it nucleus, like raisins in plum pudding. So we call this model the Plum-Pudding model. So this model has been proved to be incorrect, okay, because it means the electrons are just in the atom, okay, every part of the atom, so they can be anywhere of the atom. So this has been proved to be incorrect. So we call this model the Plum-Pudding model. Okay, and it assumes that the atoms are just positively charged lumps of matter with electrons embedded in them, okay, like raisins in a fruit cake. Okay, so but we now know that the real atom is quite different from J.J. Thomson's explanation of the structure of the atom. Then another scientist that tried to explain the structure of the atom is Ernest Rutherford, one of the foremost physicists. So he directed two of his students, Geiger and Marsden, that they should observe this alpha scattering of particles past 90 degrees. So what did he ask them to do? He asked them to take an alpha particle source, that is a radioactive material that can emit alpha particle, that they should pass the alpha particle through lead. You know, if you want to stop alpha particle, you can stop it by lead. So you just create a hole in the lead, so that the alpha particle will be monochromatic. It will just be one line. So and to be able to pass, it will pass through the lead since we have created a hole. If there is no hole, it will not be able to pass through the lead. Then there is this metal foil. So this metal foil will reflect the alpha particle, and we have a screen here. Okay. Then this is a microscope, so we can see through this microscope. This microscope takes the data actually. So this screen. So what will now happen is if the alpha particle strikes the metal foil and it gets reflected and it strikes this screen. So what we were expecting was that there will be no scattering of the alpha particle. Okay, the alpha particle that is reflected, there will be no scattering of the alpha particle when it passes through this screen. Okay, so what was observed was that although most of the alpha particles, okay, they pass through, most of them pass through, but there were some of them that were deflected at great angles, at angles that are more than 90 degrees. In fact, some of the alpha particles were sent back, okay, in their original direction. You know, when they get reflected like this, they get to the screen, but some of them, a few of them actually, were sent back. So it means there is back scattering. That is, they were scattered at angles more than 90 degrees, 180 degrees actually, 180 degrees. So they came in like this and they were reflected they were deflected back. So although that was observed for a few of the alpha particles, so this gave this data, that's Yahya and Marsden, they gave the data to their supervisor Rutherford, and his own interpretation was that the atom can never be described as a plum pudding model, like J.J. Thomson explained. He said that the atom is made up of a central heavy nucleus. So the nucleus is at the center and it is heavy. That is why the alpha particles were deflected. A few of them were deflected back across their original direction. But that most of the spaces in the atom, they were what? They were empty. And that the electrons were revolving around the atom. So this was Rutherford's interpretation of the structure of the atom. So this is Ernest Rutherford on the right. So, and he was talking with Radcliffe, okay, who is standing on the left in the Cavendish laboratory. So it's a famous laboratory, Cavendish laboratory. So you can see this sign, talk softly please. So what does that mean? It means the machines they were using were very sensitive to vibrations, and you know sound is a wave. So if you talk loudly, so it will affect some of the readings if you are carrying out an experiment. But of course, as it is written in some books, Rutherford didn't care about this notice, because he was of the mind that it didn't matter to him. Okay. Now, so the Rutherford, so we started with the Thomson's model, okay, and we said it's an incorrect model, that it's not possible for the electrons to be distributed the way they were distributed in the J.J. Thomson's model. And we said Rutherford gave a better interpretation, that the atom is made up of a central nucleus and the electrons revolve around the atom. But his own explanation, that is Rutherford's explanation, was good, but it was not perfect. There were lapses. For example, if the electrons are moving around the circle, okay, moving around the nucleus, and the electrons are negatively charged, so they are charged particles. And according to electromagnetism, if a charged particle is moving in a circle, it will radiate energy. So if the electron, so let me demonstrate. So if you have, this is the atom, and you have the nucleus at the center, and you have the electron here. The electron is negatively charged. Okay, so it's a charged particle. So if it's moving in a circular path, a charged particle will lose energy. So if it loses energy, it will lose that circular path. It will continue to lose energy until it eventually gets collapsed inside the nucleus. And if the electron gets collapsed inside the nucleus, then it means there is no atom. So if there is no atom, there is no material and so on. There is no molecule, nothing. So we know that that interpretation is not correct. Okay, so Niels Bohr, so he had some discussions with Rutherford. In fact, he went to Rutherford's lab and had some discussions with him, and after that he published his own papers. So he gave certain assumptions. So in his interpretation, number one, that the electron moves in orbits around the proton. Of course, this is what Rutherford also explained. And that the electric Coulomb force provides the needed centripetal force. I'll talk about this later. Okay, so the electron, they move, let me slide show. Okay, so the electrons move in orbits around the nucleus with the electric force provided in the centripetal, because if an object is moving in a circle, it needs centripetal force. Okay, the centripetal force is mv squared over r. Okay, so the energy that keeps the electron to be moving in that circular path is provided by the centripetal force, and is provided by the Coulomb force between the electron and the what? Proton. According to Coulomb's law, the force between two charges is proportional to the product of the charges. So the first charge is minus E, the second charge is plus E. Electron has charge minus E, proton has charge plus E, and the distance between them is what? Is r. This K is a constant, which is 1 over 4 pi epsilon naught. Okay, so the centripetal force is provided by the Coulomb force between the electron and the what? And the proton. So the first interpretation of Bohr gives rise to equation 1. Then now the orbits in which the electron moves, they are stable. Okay, unlike the Rutherford's interpretation that the electron, because if the electron is a charged particle, if it's moving in a circle, it will radiate energy. So Bohr said that the electron does not radiate energy. Okay, so the energy is what is constant. So this gives a better interpretation to the Rutherford's model. But radiation can be emitted or absorbed. Okay, radiation can be emitted if the electron jumps from a higher state to a lower energy state. So the electrons, the energy is radiated. Then energy is absorbed if the electron moves from a lower energy state to a higher energy state. So radiation is only emitted or absorbed when the electron jumps from one orbit to another. And of course, the wavelength of radiation or the frequency of radiation depends on the energy of the electron in both the initial and final orbits. Again, this gives rise to this equation 3, that the energy that is emitted when an electron jumps from one level to another is given by this. So it's related to the frequency. H is Planck's constant, F is frequency, and lambda is what is wavelength. Okay, so that interpretation gives rise to equation 3. Then the allowed orbits, they are those for which the orbital angular momentum is an integer multiple of h bar. Okay, so only certain orbits are allowed. So what that means is that the electron cannot just move like a spiral and collapses and get collapsed into the nucleus. No, that if this is the structure of the atom, this is the nucleus. Okay, that there are only certain levels that are allowed. Only certain levels are allowed. So the electron can move from this level to this level. Okay, the electron can move from this level to this level, or from this level to this level, and so on. Okay, there are higher levels, of course. There are higher levels. So the electron can move from one level to another. So the closest level to the nucleus is what we call the ground state. So the energy it has, this is the nucleus. Okay, this, let me color the nucleus red. So the nucleus, this is the nucleus in red. So the lowest orbit is this one. This, let's call it 1. This is the second orbit, 2. This is the third orbit, 3. This is the fourth orbit, 4. This is the fifth orbit, 5. So the lowest orbit is when n equals 1, principal quantum number equals 1, and the energy the electron possesses at that point, we call it the ground state energy. The ground state energy. So only these orbits are allowed. The electron cannot be in between. It cannot be here. It cannot be at this point. It's not allowed. Okay, so that's not allowed. It can only be at this orbit, or this second orbit, or this third orbit, or this fourth orbit, or fifth orbit. It cannot be in between 3 and 4, and it cannot be in between 4 and 5. So these interpretations are very, very important, and they form the foundation of our understanding of modern physics, so the atomic structure. So I've explained this before, that the centripetal force, that is the energy that keeps the electron to moving in that circular path, so it's provided by the Coulomb force between the electron and the proton. So the centripetal force is provided by the Coulomb force. Now we can prove that the total energy, the energy the electron possesses in a particular energy level, is given by this equation. Okay, minus 13.6 electron volts over n square. So this n is a principal quantum number, so it can take 1, 2, 3, 4. Okay, like I explained here. So the lowest orbit is when n is 1, the second one is n is 2, 3, 4, 5, 6, 7, and so on and so forth. So the lowest orbit is obtained at when n equals 1. So when n equals 1, then we have E1 equals minus 13.6 divided by 1 square, which will be minus 13.6, and this is what we have here. So this is the energy level diagram. Okay, of course this is for hydrogen. Okay, so if an electron moves from this level, n equals 2 to n equals 1, so the energy that will be radiated is what? 13.6 electron volts. 13.6 electron volt, because the formula is the energy equals minus 13.6 over n square. This is n equals 2. Okay, so this n equals 2 means that the energy will be 13.6 divided by 2 square. What is 2 square? 4, and that is 3.4. Then the next one, n equals 3, so that will be 13.6 divided by 3 square, which is what? 9, and that is 1.51. So and so on and so forth till it gets to infinity. Okay, you can see 1, 2, 3, 4, 5, 6, 7, 8, and so up to infinity. At infinity, the energy is what? Is 0. What does that mean? It means the electron has escaped from that Coulomb force that ties it to the nucleus. Okay, so if you want to remove the electron from orbiting the nucleus, so the energy that you need to supply is what? Infinity. 0. So at that 0, so the energy the electron possesses at n equals infinity is what? 0 electron volts. So because the electron has escaped from the nucleus, so the energy that you need to supply to do that is what we call the ionization energy. All right. Then this is the same diagram, but let me explain something here. So I said the permitted orbit. So this is the nucleus. This is n equals 1. Okay, n equals 2, n equals 3, n equals 4, n equals 5, and n equals 6. The nucleus is the big black dot. So when there is a jump from maybe n equals 2 to n equals 1, or n equals 3 to n equals 1, or 4 to 1, okay, we call that series the Lyman series, and it is found in the ultraviolet. The energy emitted is found in the ultraviolet region. When it is from any other orbit to n equals 2, they will call it the Balmer series. When it's from any orbit to n equals 3, we call it the Paschen series. When it's from any orbit to n equals 4, we call it the Brackett series. And when it's from any arbitrary orbit to n equals 5, we call it the P-Fond series. So we have the Lyman, Balmer, Paschen, Brackett, P-Fond. Again, Lyman, Balmer, Paschen, Brackett, P-Fond. So these are the energy levels of the electron in the hydrogen atom. Okay, so let's take a look at this simple problem. So the question says, what is the wavelength that is emitted for the first Balmer line when a hydrogen atom makes a transition from the n equals 3 to the n equals 2? Okay, so transition from n equals 3 to n equals 2. That is Balmer series. Okay, first in the Balmer. So it means the wavelength we will get, the wavelength will be between the visible light spectrum and the ultraviolet. Okay, so what we do is, to get the wavelength, we calculate the energy at n equals 3 minus the energy at n equals 2. Then we equate the formula, we equate that to hc over lambda. Okay, use the equation 3. So the final energy minus initial energy equals hc over lambda. Then from there we make lambda the subject of the formula. That is, we have the energy, okay, equals hc over lambda. Then we make lambda the subject of the formula, so that we have lambda equals what? hc over the energy. So when we calculate the energy that is emitted from moving from n equals 3 to 2, then we now say h multiplied by c, then divide by that energy. Okay, so and that is what we do here. So lambda equals hc over the energy that is emitted. So the formula for the energy is minus 30.6 over n squared. So the initial n is 3 squared, so 3 squared, that is 9. Then the final n is 2 squared, so 2 squared, that is what? 4. So if you evaluate this, so let's take out our calculator to evaluate this, so that we have 13.6 minus 13.6 multiplied by 1 over 9, then minus 1 over 4. So we get 1.88889. So that's approximately 1.89 electron volts. So then to now calculate the wavelength that is emitted, so we use hc over delta E. The h is Planck's constant, which is 6.63 times 10 per minus 34. C is the speed of light, which is 3 times 10 per 8 meters per second. This is joule second. Then divided by 1.89 electron volts. So you have to convert 1.89 electron volts to joules. How do you do that? 1 electron volt, okay, 1 electron volts is 1.6 times 10 to the power minus 19 joules. Okay, 1 electron volt is 1.6 times 10 to the power minus 19 electron volts. So what you do is you take out your calculator, you can create numerator divided by denominator. The numerator, we have 6.63 times 10 to the power minus 34, then multiply by 3 times 10 to the power 8, then divided by 1.89 divided by 1.89 times 1.89, okay, yeah, times 1.6 times 10 to the power minus 19. Okay, so and you have 6.58. So 1, 2, 3, 4. Okay, let me put it in standard form. Okay, anyway, so this is 1, 2, 3, 4, 5, 6, 7. So that'll be 6.58 times 10 to the power minus 7 meters, which is 658 nanometer. 1 nanometer is 1 times 10 to the power minus 9 meters. So the wavelength that is emitted is 658 nanometer. You can see it is between the visible spectrum and the ultraviolet. Okay, so that's about that. Now the Bohr model, okay, successfully explained the structure of the atom, but of course it's not a perfect model. So it has explained. You can use it to explain the hydrogen atom and hydrogenic atom. Okay, but when it gets to many electron atoms, so there's a problem. So that is why we use actual quantum mechanics for that, but we will not talk about that in this course. Okay, so the hydrogen spectrum. So let's just focus for now on the hydrogen atom because it's the simplest atom to study. So it has just 1 electron. So it is composed of a nucleus and 1 electron. So many theorists, so they start by first explaining the hydrogen spectrum. So if you consider the hydrogen atom, all the energy or all the wavelengths that are emitted, they can be described by this simple empirical formula. Okay, this simple formula. So some people call it the Rydberg formula. Okay, 1 over lambda equals r into bracket 1 over nl squared minus 1 over nu squared, where this r is a constant, the Rydberg's constant. You can write it as 1.096778 times 10 to the power minus 3 per angstrom. So this formula can be used for all the series that I explained here, the Lehman series, the Balmer, the Paschen, the bracket P fund. Okay, now for the Lehman series, that is n equals 1, that is nl equals 1. For the Balmer series, nl equals 2. For the Paschen series, nl equals 3. For the bracket series, nl equals 4. And for the P fund series, nl equals what? 5. So these were the 5 that were given names. Okay, so the Lehman series, nl is 1, the Balmer nl is 2, the Paschen nl is 3, the bracket nl is 4, and the P fund nl is 5. But the upper n, okay, for the Lehman series starts from 2, so it can be 2, 3, 4, 5, 6, 7, 8 up to infinity. For the Balmer, it will start from 3, 4, 5, 6 up to infinity. For the Paschen series, nl is 3, so nu starts from 4, 4, 5, 6, 7, 8, 9, 10, and so on. For the bracket, nu starts from 5, 6, 7, 8, and so up to infinity. And for the P fund, nu starts from 6, 7, 8, 9, 10 up to infinity. Now, if a question asks you to calculate the energy or the wavelength that is emitted when maybe for the first line of the Lehman series, first line, this is the first line, nu equals 2. First line for the Paschen series, nu equals what? 4. If the question says second line of the Paschen series, so when you talk about the second line, so for example for the Paschen series, so nu will be 5. And we'll talk about the third line, nu will be 6. Okay, so the first example for today, Determine in angstroms the shortest and longest wavelength of the Lyman series of hydrogen. So we use the formula. So we have to calculate the shortest wavelength as well as the longest wavelength. Now for the Lyman series. So the Lyman series, NL is 1, while NU starts from 2, 3, 4, and so on. Okay. So the longest wavelength is obtained at NU equals 2. The same thing, if you are asked to calculate for Balmer series. For the Balmer series, the longest wavelength will be obtained at NU equals what? 3. While the shortest wavelength is obtained for all the series at NU equals what? Infinity. Okay, so if you are asked to calculate the shortest wavelength for any of the series, so NU will be what? Infinity. So let's start from the longest wavelength. For the Lyman series, NU will be what? 2. For the Balmer, it will be 3, and so on and so forth. So you have 1 over lambda maximum equals the R, which is 1.097 times 10 minus 3 per angstrom, then 1 minus 1 over 2 squared. So that will be 1 over 4. 1 minus 1 over 4. Then multiply by this. Then you will now find the inverse. So what do I mean? You first, so you multiply 1.097 times 10 raised to the power minus 3, multiply by, open bracket, 1 minus 1 over 4. 1 minus 1 over 4. And what is 1 over 4? That is 0.25. So after getting that, then you find the inverse to get, because that answer will give us 1 over lambda max. Then you now find the inverse of that to give you lambda max, and you get 1215.4 angstrom. Now please, you should note that this angstrom, it means what? 1 angstrom is what? 1 times 10 raised to the power minus 10 meters. Okay, 1 nanometer is 1 times 10 raised to the power minus 9 meters. Okay, so 1 angstrom is 1 times 10 raised to the power minus 10 meters. Is that clear? Okay. So the maximum wavelength is obtained as 1215 angstrom. Then the shortest wavelength is obtained at NU equals infinity for all of them, for all the Lyman, Balmer, Paschen, bracket, Bfon. The shortest wavelength is obtained at NU equals infinity. So you say 1 over 1 squared, which is 1, minus 1 over infinity squared. What is infinity squared? Infinity. 1 divided by infinity, 0. 1 minus 0, 1. 1 multiplied by this will give you the same value. Then you find reciprocal of this to give what? 912. So that is, you find reciprocal of so you say 1 divided by 1.097 times 10 to the power minus 3. Then you obtain 911.577, which is approximately 912 angstrom. Okay, so you should know that again, this Rydberg's constant, we have written the Rydberg's constant as we gave it as 1.097 times 10 to the power minus 3 per angstrom. We can also write it as 1.097 times 10 to the power minus 7 per meter. We can also write it like this, per meter. Okay, so that in this case your answer will be in meters. In this case your answer will be in what? In angstrom. All right. Then the second example says that determine the wavelength of the second line of the Paschen series for hydrogen. So I explained previously that when they say first line of the series for Paschen, for example, NL is 3. So the first line will be NU equals 4. The second line will be NU equals 5. The third line will be NU equals 6. So in this question we are asked to calculate for the second line. So the second line NU is what? Is 5. Okay, so that's our formula. So we have 1 over lambda equals R multiplied by 1 over 3 squared minus 1 over 5 squared. And if you evaluate this lambda, you obtain approximately 12819 angstrom. Okay, so you can check that. Okay, so for your assignment, so you have to assign assignment, Number one is to explain Heisenberg uncertainty principle. Number two is to explain the de Broglie wavelength. So you give examples as well to illustrate this. All right, thank you. So we'll stop here for today. Thank you. See you later.